integral 0 to L k lambda dx all over x0 minus x all squared. Alright, and now k lambda is a constant that can come out. Let's do this integration. K lambda is a constant that comes out. Integral 1 over x0 minus x all squared dx. Can you integrate this on your own? Well, you can do this by using a little substitution. And that will give you, I'm going to give you the result. I'm going to leave you to do the integration on your own. Integral of 1 over x0 minus x squared is actually 1 over x0 minus x. And the lower limit is 0, the upper limit is L. If anybody wants explanation on how it is integrated, write to me. But I would expect most of you to know this. You see, I will give you a clue. The clue is this. Integral of 1 over x squared dx. You know that it is negative 1 over x. And now, if you notice that negative sign, the negative x squared will make that positive. So integral of this quantity will be 1 over x0 minus x with a positive sign. x0 is a constant. Alright? And now we replace x by L, the upper limit, minus replace x by the lower limit 0. Is that right? So that will be k lambda times, using the upper limit, this becomes 1 over x0 minus L. This is the upper limit, minus, put x equal to 0 for the lower limit. What does that become? That will be k lambda times 1 over x0 minus L, and this will be now 1 over x0, and I take x0 times x0 minus L as the common denominator. You see that? This is just x0. If you now take x0 times x0 minus L as the common denominator, the numerator will be x0 minus x0 minus L. And what does that become? x0 minus x0 will cancel. So the numerator will be positive L over x0 times x0 minus L. And now we can bring in the k lambda L right up there. You can see that will be k times lambda L over x0 times x0 minus L. Why did I color lambda L? Because lambda is charge per unit length. If you multiply that with the length L, that is a measure of the total charge on the extended charged object. So this will be kq over x0 times x0 minus L. This is the expression for electric field at a point on the axis of an extended charged object like this. Now, let's do some approximations. When P is very far, now if this is the charged object and you take a point very far, say if I'm standing at Port Charlotte, take a point in Fort Myers, then you know that x0 minus L will be approximately x0. Then compared with that distance, the length of this object will be very small. So when the distance is very large, this x0 minus L can be approximated to be x0. Then what will this equation become? It will become E equal to kq over x0 squared. In other words, you can see when the distance is very large, this object will behave like a point charge. Isn't this the equation for the field due to a point charge? Yes. Okay. a point very far from the object behaves like a point charge. And that is true for any extended object. When you take the points very far from the object, the extended object can be considered to be a point object. I think you can understand that point. Let's do an example. A uniform line charge of charge density lambda equal to 3.5 nanocoulomb per meter extends from x equal to 0 to x equal to 5 meter. What is the total charge on it? Find the electric field at x equal to 6 meter, x equal to 9 meter, and x equal to 250 meter. Alright, we got lambda equal to 3.5 nanocoulomb per meter and the length equal to 5 meter. Therefore, Q, the total charge on it, is L times lambda, which is 5 meter times 3.5 nanocoulomb per meter, and that is 17.5 nanocoulomb is the total charge on it. Well, now we need to find the electric field at x equal to 6 meter. Tell me, to find the electric field at x equal to 6 meter, do we use the actual formula or the approximate formula? Well, our x0 equal to 6 meter. Well, we need to use the exact formula. E equal to kq over x0 times x0 minus L. Now we know k, we now know q, the amount of charge on it. We know our x0, we know our L. Replace all those values. That will give you the field as 26.25 Newton per Coulomb. Alright, in the next case, we need to find the field at x equal to 9 meter. Now, can we use the approximate formula there? No, 9 meter is not too far from a charge of length, how much? 5 meter. The length of the charged object is 5 meter. So 9 meters from one end is not very far. We still need to use that exact formula. So to find the field at x equal to 9 meter, not 6, it has to be 9 meter. We use x0 equal to 9. So the same formula, the only difference is x0 now will become 9. There you are. So replace your k and your q. You know we calculated the q. x0 is 9 and that now equal to 4.4 nanocoulomb per meter, Newton per Coulomb, the electric field. How about D? Find the electric field at a distance 250 meter. Well, that's quite considerable. That means we can use the approximate formula. What is the approximate formula? X equal to 250 is very large compared to L equal to 5. So we use the approximate formula E equal to KQ over X0 squared. Well, we know all these values. We know K, we know Q, we know x0, which is 250. And using those values, we get the electric field as 0.0025 Newton per Coulomb. Okay, let's now look at another type of